Thank you, Lin. And yes, in this presentation, I will try to give you some insights about control strategies of molten salt reactor. Especially, I will focus on the first part, so on control, because I don't know if you have some knowledge about control. So let's start with, let's say, a step-by-step procedure. I will introduce you with some general knowledge about control, and then I will speak about control in a nuclear reactor, and then we'll go for the control in molten salt reactor. So, what control means? A control problem deals with all the action that we have to perform to obtain a specific behavior from a system. We have our system, which can be, in our cases, our nuclear reactor, and we have some inputs and outputs, and the inputs are all the variables that we can act in order to change the behavior of our system, and the outputs are the variable that we want to keep in a certain range, or we are interested in. Actually, there are other variables we are called the state variables, which are inside the system that characterize the system, and actually they can be not accessible. I mean, I can have a variable that cannot be an output. This is the typical case of the reactivity in nuclear reactor. We don't have a reactivometer in order to direct measure the reactivity, and so in this case, reactivity cannot be considered an output. So basically, the problem involves the system to be controlled. We have to study the system, and we have to study our desired behavior. Usually, we want to keep our control variable as close as possible close to a set point. So the aim of the control is try to perform an input action in order to limit the error, so the difference between the actual value and the set point. In order to do this, we have to design a controller and also to implement a control law. Actually, in every moment of the day, we deal with the control problem. Just think about your cat. His output is maybe it wants attention because it is hungry, and so you can feed him with some pizza or something like that in order to limit its complaint. Actually, we can think about other engineering problem like the heating of your house. In this case, the control problem is try to control the temperature in the house. The controlled variable is the temperature in the house, and the set point is the reference temperature. How we can obtain a constant temperature in our house? We can act on the heat production of our boiler or furnace. Why control is important in general will be also important in nuclear? Because in this way we can make the system work in a safe way. So we want to be able to act on our system in a safe way. We want to fulfill the performance specification and the other operational constraint. We have other additional purposes. For example, we want to limit the influence of external disturbances. In our system, there is no system without disturbances. All our systems are affected by disturbances, and we want to limit their influence. In addition, we want to ensure the stability of the system. We don't want that our control action make the system unsafe. And then obviously we want to at least try to optimize the performance of our system. Mainly we can think about two types of control, manual and automatic. Just think about that when you are when you drive your car, actually what you do is try to keep a safety distance between your car and the car ahead, and so you can control the velocity of your car in order to keep this distance, let's say, safe. We have basically two kinds of control: the feed-forward control, or the open-loop control, and the feedback control. In the first one, basically, our control action, which is performed by a tool, a controller, is insensitive to the actual value that the variable that I want to control assumes. So mainly the controller is based on a system model that tries to reproduce the behavior of the system and does not depend on the output. On the other hand, we have the feedback control. In this kind of control, we take the output and we use the actual output in order to tune our control action. Actually, there is some differences, obviously, between the two. The feed-forward does not need any measurement of the output, but on the other hand, we have to pay the cost to have an accurate modeling, because since we have no information from the output, we need other information from somewhere, in this case from the model. The other difference, okay. The other difference is that in the first case, we have a high impact of the disturbances. This because we cannot consider the disturbances in our system model. On the other hand, in this case, the disturbances are considered because obviously the disturbance will affect the actual value of the outputs, and so the controller can dump these disturbances. If we go back to the heating system, we can think a feed-forward control in the sense that we can turn on and turn off our heating system in some hours. So we don't feed the controller with some information about the temperature, but we just turn on and turn off our heating system in a certain hour. On the other hand, we can think about the feedback control in the heating system, just where there is a thermostat that can control the temperature. So we have a sensor that measures the temperature and can activate or not our heating system according to the temperature, to the actual temperature. The other problem is that how we can communicate with the controller. We need measurement and we need actuator. The first one provides the controller with the value of the output. In our cases, for example, is the sensor of the temperature. The actuator instead tries to transform the control action that the controller decides to implement in order to achieve the control aim with an effective control on the system. So obviously also the measurement and the actuator are affected not only by uncertainty but also by malfunction. So when we want to design a control system, we have to keep in mind both of these problems. In particular, how to implement a feedback control. Basically, we want to keep the actual value and desired value as low as possible. So at the end, this is E is the actuating, should be 0. Actually, cannot be 0 for all the time, but we will try at least to limit in acceptable limits. Okay, question times. And I think you are tired, so I'm not obliged you to answer to this question. But it's quite strange to think about in what year was the first application of the feedback control. Or actually, we can think about in which century was the first application. And actually, it's the 3rd century before Christ. And this is a water clock of a Greek inventor which used a float regulator in order to control, to have a kind of feedback on this system. Actually, this is a water clock, so from a regulating vessel, the water trickles from an orifice, and here there is the measuring vessel, and we can have the time goes by with the time scale. The problem, the control problem in this case, is to ensure a constant water level in order to have a constant velocity outside here. And how this Greece guy tried to implement this control? He used a float. So in this case, he tried to control, to keep this the level of the water as constant as possible, because if the level goes down, this float allow to some water flow rate will go down from a reservoir, and then when the level is too high, this float will close this hole in order to stop the mass flow rate. So we can also depict this feedback system with this graph. So we have, this is the feedback mechanism, so the float that try to regulate the error, so the actual value and the desired value, and the valve try, which is the controller, try to give the correct input to the regulating vessel. So it's not a new concept, the feedback system. Going to the more engineering example, the first automatic feedback control was used in industrial process, and was the James Watt's flyball governor. It used this tool in a textile mile when we have wheels and loops connected each other with some belt drives. In this case, the control problem is try to keep the velocity of the steam engines as constant as possible in order to avoid some problem with the looms. They saw that when a loom is added, the engine speed decrease. So they invented, in particular James Watt invented this ball governor. So in case that the engine speed increase, this ball swing out, and then the throttle valve reduce the steam flow which enters in the steam engines, and then the engine speed decreases. So it's a real feedback control that was implemented the first one in the automatic controller. Actually, this is more or less the same that happens in electrical grid. So in order to keep the frequency of the electrical grid constant, actually what this can be affected, the frequency, by load and by power plant. Actually, if a load is added in an electrical grid, the frequency of our electrical grid decreases. So in modern power plant, there will be a controller that acts on the valve, on the turbine admission valve, in order to regulate the power. Okay. There is obviously some drawbacks when we talk about feedback control, and the main drawbacks is that it may create instability. The action that we perform on our system may cause some instability. And since this instability is mainly a dynamic phenomenon, we have to get some information from the system from a dynamics point of view. Actually, you can have two kinds of instability. The first one is the equilibrium stability. So, for example, this is our set point, and then in a certain time a disturbance happens, and if we have a stable system, the system will reach again the same set point. Otherwise, some oscillation will start, and then our system will continue to to oscillate to some unacceptable value. On the other hand, we have also the stability of the system. In particular, this is related to when we change some input of our system. We want to bring our system from a set point to other set point, and obviously the best way, the way that we want to achieve, is this smooth achievement of the new set point without some overshoot or without some unstable behavior. So the stability can be studied just if we model our system. So you can see that in this case, control and also modeling is very connected, are very connected. In particular, if we add a feedback on our system, we can have different behavior. We can have a negative feedback. So if, for example, we want to increase the level of our variable, the controller, or better, in this case, the feedback, generate an action on the system so as that this variable decrease. So we have a stable feedback. This is the case, the most case in nuclear reactor, when we want to have some negative reactivity feedback. On the other hand, we may have some positive feedback, which is very bad in our cases, because in this case the transient continues to increase, and we may lose the functionality of some system. This is related to the natural feedback that a system may have, but if we add a control system, we are adding basically a feedback. And what is important is that the stability of the feedback system, so the controlled system, is not granted even if the system is stable. So we have to pay attention when we design controllers, because we have to ensure that this may create some instability. So the aim, as I told before, is try to design a controller and a control laws. Basically, if we speak about feedback control, we want to design this law. So a function of the error that generates some inputs. The most famous controllers are the PID controllers, are controllers that are formed by a proportional action, proportional to the error, an integral action, and a derivative one. In nuclear system, usually we have just PI controllers and not PID, because this term is quite dangerous. Just think about if we have a very steep increase of our error, this make the controller action skyrocketing due to the derivative. So we obviously go very carefully when we talk about nuclear, so we usually don't consider derivative action. Which are the several phases of the control design? We have to establish some control goals. In our cases, for example, the temperature that should be constant. Then another important thing is the so-called pairing selection, so what controls what. We have a lot of controlled variable or variable to be controlled, but usually we have few control variables. So we have to find the best matching between them in order to ensure our control goals. Then we have to study the system configuration, in particular in the modeling of the system. And starting from the modeling of the system, we can have some information on how to implement our control action. And so we can modeling our controller and then optimize all the system. But just go to the nuclear part. What controlling a nuclear power plant means? We want to regulate. The main aim in nuclear power plants is to regulate the reactor power according with the system demands, which came from the electrical grid or from the, for example, the regulatory body, in a consistent and constrained way. We have to maintain the energy balance between all the several loops that characterize the plant reactor. So we here the energy comes from the nuclear fuel to and is delivered to a coolant. This is the here we have the steam production, and then we have the turbine and the generator. So we have to consider the nuclear power plants from the neutron in the core to the electron in the grid. And actually we don't want only to control the power, but we have to ensure optimum working condition also for the controlled variables in order to avoid the protection system and the safety system to shut down the power plant. So, for example, here you can see that we have separate function from safety and control. So when we want to design this part, we want that these guys don't act on our system because we are failing to control one of our variable. When we talk about nuclear power plant as control variables, we can think about fission, heat transfer, flow, pressure, some temperature. Actually, we have usually very few control variables. Mainly the most important are the control rods, but we can have valve or pumps in order to control our mass flow rate. Usually in nuclear power plant we have some different control loops. We have a lot of control variables, some control variables, and we want to match what control what. So the control loop is the loop between the controlled and the control variables. This is more or less the control loop that are present in a PWR. So we have the reactor nuclear power control, the pressurizer control, the boiler level control, the boiler pressure control, and then turbine load control. Just to have an example, the pressurized control want to keep the pressure inside the primary coolant as constant as possible. This is done acting on the pressurizer, so on the heaters inside the pressurizer or just the sprayers inside the pressurizer. If you remember the James Watt flyball governor, the aim is try to control the power of nuclear power plant. Usually, the nuclear reactor, or better, the pressurized water reactor are turbine leading reactor or reactor following. This means that they are able to autonomously change their power according to the new set point dictated by the turbine load control. So this means that if we want more power in our nuclear power plant, we open the governor valves in order to admit more mass flow rate in our turbine. This means that we are lowering the pressure inside the steam generator. So this means that we are lowering the temperature, and lower temperature means that if our reactor has some negative coefficient, the power goes up. So this is not enough in order to control the power in a nuclear power plant. This means that our reactor is a good candidate to perform load following, but we have to keep in mind that we have also to control the other variables. We want to increase the power, but we want that the other variables to be kept in a narrow range with respect to their set point. Obviously, a nuclear reactor does not be at full power. We have different control mode. We have the startup, we have the shutdown, and other operational mode. Just think about the startup, which is all the action needed to bring the reactor from a cold shutdown to a hot operating status, there is a lot of control action that should be that has to be coordinated. And here you can see a kind of map of the startup of a PWR. These are the temperature of the primary, and this is the pressure. We have to ensure that our, let's say, path to full power is inside some stable region of this two variable graph. So actually the control action to be performed are quite long. We have to make some precritical checklist. We have to ensure some the chemistry in the steam generator. We have to ensure that all is okay, and then we can start up with increasing pressure and temperature with coordination between the pumps and also the pressurizer. When we want to design a control scheme, a control strategy for nuclear reactor, we need a simulation tool both for the realization, for the testing, and for the validation. So the control field is a kind of multi-step and also multidisciplinary field. We start with studying some governing dynamics of the system, so we have to study the system and see how it reacts, changing some input, and we saw which is the behavior of the output. Then this can provide us with some interesting information for the pairing selection, so what controls what. Then we can implement our control scheme, so we design our controllers in order to be stable, in order to reach our purposes. And then we can define the several operation modes, so startup, full power, and shutdown modes. And then these will be included in the master control scheme design that decide all the modes that should be run in the nuclear reactor. So in this case for control, as I said, the control-oriented simulation is very important. The first aim is try to evaluate the stability of the system in the entire power range. So we want to have some dynamics response to typical transient initiator, and this provide us some guidelines to the conception of the control system. Usually we start with a very basic equation. This is usually done because we are interested in some dynamics, in the governing dynamics. If we use some more, let's say, accurate modeling, the problem is that when we discretize an equation, we introduce some numerical information that are not related to the system. So we may have some problem because we are considering some numerical behavior as physical behavior. Usually the stability is studied considering a very simple system. In this case, we want to study the eigenvalues of our dynamic system, and so the condition for this asymptotic stability is that all the poles lays on the negative half plane, real half plane. Going to the molten salt reactor, okay, we know that it's very promising, but there is some but. There is very little experience compared to the present nuclear reactor system. The fuel motion is not common in other nuclear reactors, and the standard nuclear codes for simulation are not suitable. Since this does not mean that they are not good, simply they are not tailored on the modeling needs of the present generation of nuclear reactors, in particular for molten salt reactor. Actually, there are two main issues that affect the control of the molten salt. One is the drift of delayed neutron precursors, because we have an impact of the beta effect, the effective beta, and on the dynamics, and so on the control features. The second one is we have a strong coupling between neutronics and thermal hydraulics, and it requires dedicated tools for simulation analysis. So, what we can say? We can say that control strategies that are retrieved from light water reactor and sodium fast reactor are not suitable. We have a different reactor with different issues, so we have to design different control strategies. Basically, this is a very, very simple model, point kinetics model. Going back to the question, can we use the point kinetics in modeling the molten salt reactor? It depends on your needs. For getting the physics of the problem, point kinetics is sufficient. Here you can see the impact on the precursors equation of the precursors that leave the core and the precursors that re-enter in the core since they not decay in the external loop. The main problem is that in steady state case, we have a decrease beta as shown before due to the drift of the precursor. So since the beta is relevant for control because it makes the dynamics of our nuclear reactors lower, so also controllable, we have an impact on the control feature since this is the reactivity loss due to the velocity change. This means that if we are considering the startup and the shutdown of the molten salt reactor, we are basically changing during this system the beta. This is not so bad for the shutdown since we, let's say, gain from a beta point of view, but for a startup point of view, we have to pay attention because when pumps start to run, we have a decrease of the beta, so the decrease of the margin to the prompt criticality. This is the impact of the circulating fuel on in our equation. Basically, we have a nu in our equation. From a zero power point of view, the kinetics is quite different from static and the circulating fuel. You can see here, this is the dominated pole of the behavior of the kinetics. For the static fuel, we have for a zero reactivity, we have a constant behavior, but it's not the same for the circulating fuel. From the same level of the reactivity, we have different dynamic response. And this should be taken into account, especially when we are considering strategies for the startup. What happens if we add temperature feedbacks? I have 5 minutes, okay. What happens if we add temperature feedback? We know that in a molten salt fast reactor we have two strong negative feedback, the Doppler one and the density effect. But for example, for the molten salt breeder reactor, we have also some positive effect, which is due to the graphite. And in this case, in particular for the thermal concept, we have to consider to take into account the balance between the two effects. So this is simply a kind of line that separates the unstable and stable region, considering the fuel, the salt reactivity effect, and the graphite effect. And these are the movement of the pole which indicated us where the system is stable or not. The system is stable if the poles lays in this zone, and we can see that if we increase, if the effect of the graphite predominates, we have an unstable system. One of the main concern about molten salt reactor is that we have very few experience and how to make the pairing selection, so what controls what. Actually, what we can do is try to find a way to have the best coupling between control and controlled variable. This could be made with an algorithm, the relative gain array, in which we treat our system, which is multiple inputs and multiple outputs. We have several inputs that affect our system and in turns affect several outputs. We treat as the classic strategy used in the PWR. So we implement several uncoupled single input, single output system. So this is basically a technique in order to select which is the best variable to control another one. And for example, in the molten salt reactor, we have the main control variables are the power, the inlet core temperature, the outlet core temperature, and the outlet temperature of the intermediate salt. And we have, no, this is switched. These are the control variable, and these are the controlled one. And as for the control, we have control rods, but not in molten salt fast reactor, and basically the flow rate and the inlet temperature of the energy conversion fluid. So thanks to this technique, we can try to find the best pairing between the control and the controlled variable in order to select the correct pairing. But as I said before, what happens if we don't have control rods? Control rods are the main control variable that we have in a conventional reactor. Actually, this refers to a study performed during the EVOL project. Actually, we are able to manage the power and the temperature of the fuel, the outlet temperature of the fuel or the inlet temperature of the fuel, acting on the mass flow rate of both primary and intermediate circuit. So basically, in the molten salt fast reactor, we don't have control rods, but we have strong negative feedbacks. This allows us to use the mass flow rate in order to control our variables of interest. And these are some trends of the controlled system. Here you can see the power, which is completely overlapped with the required power, and in black this is the secondary, the intermediate mass flow rate that varies according to the power change of the set point. In conclusion, we saw that control means to impose the behavior that we want from the reactor. The molten salt reactor has some special features that makes these tasks more, let's say, multidisciplinary than the conventional one. Usually we go for this multi-step and multidisciplinary procedure, and usually we have to confirm with the simulation our control scheme works. I think that the main question to be answered is that we can control our reactor without control rod. Why not? But this is just for some control aspects, not from a safety point of view. We can take advantage from the strong coupling within the neutronics and the thermal hydraulics in order to be, let's say, our fluid, our control rod, but just from a control point of view. And thank you for attention.